So let's discuss about the orthogonal matrix in analytic geometry. So definition is a square matrix of order n cross n is an orthogonal matrix if and only if its columns are orthogonal. So that we can write as A into A transpose, that is equal to identity matrix, and that is equal to A transpose into A. That means we know that A into A inverse is equal to identity matrix. So we got our A inverse as A transpose. So we can obtain the inverse by simply transposing the matrix if our matrix A is orthogonal. Transformation of orthogonal matrix are special because the length of vector x doesn't change while we are transforming an orthogonal matrix A. So this is the square of the magnitude of ax matrix, and this is Euclidean norm. We know that norm of x is root over x transpose into x. So this is ax transpose into ax, and that we can write as ab transpose as b transpose a transpose property. So it is x transpose a into x, and from the previous result a transpose into a, that is equal to I. So here we will put I x transpose into I into x. So x transpose into x, that is the norm of the x square. So the angle between x and y is given by the dot product divided by their magnitude. So this will be angle cos omega, that will be the angle between these two. So we, after solving this, we will put the value of x transpose a transpose using the properties, and a transpose a as I. We will put this value, and we got this result of angle, that is the angle between x and y. So this gives the exactly angle between x and y. So this was the whole concept of the orthogonal matrix and transformation of orthogonal matrix. Now orthonormal basis. Consider, let us consider a n-dimensional vector space V and a basis of V, that is B1 to Bn. It is orthonormal basis when if the inner product of Bi Bj is 0 in case of I is not equal to j, and when I is equal to j, their inner product is 1. If these two conditions satisfy simultaneously, then we can say that our basis is orthonormal basis. So let us consider an example, simple example on this orthonormal basis. So our dimensional is R2, two-dimensional vector. The vector are B1 and B2. B1 and B2. So it form an orthonormal basis because when we find the inner product of B1, B2, that is the B1 transpose into B2, that comes out to be 0. So it is an orthonormal basis. Now let us discuss this next topic of orthonormal complements. So consider a d-dimensional vector, a d-dimensional vector space V and an m-dimensional subspace U, that is the subset of V. Then its orthogonal complement, that is denoted by U complement, is a d minus m dimensional subspace of V. And what is its speciality? That is, it contains all the vectors in V that are orthogonal in every vector in U. So the orthogonal complement contains all the vectors of V that are orthogonal to every vector in U. That means if we are taking the intersection of U and U complement, that comes out to be nil. So that every vector x can be decomposed as, so x can be decomposed as m is equal to 1 to m, where m is the dimensional of the vector space V. M is the dimensional of the subspace U, and this is the lambda m bm plus summation j is equal to 1 to d minus m dimensional psi of j bj complement. So this is the where lambda m and psi j are any real numbers. So we can write any vector x as the decomposition of their summations. So b1 to bm is the basis of u, and b1 complement to B complement dm minus 1 is basis of u complement. So that was the orthogonal complement of any vector space V. Inner product of the functions. In the last time we have seen the inner product of two vectors. Now we will see the inner product of two functions. So let us assume the two functions. First function is u function, that is real to real. Second function is v function, that is also from real to real, can be defined as the definite integral, that is the inner product of two functions, that is the integration of definite integration of ux vx dx limits from a to b, where a and b are finite. So this is the inner product of two functions u and v. So let us take an example. If u is sin x and v is cos x, and let us assume the integrand, let us assume the integrand fx. Integrand is fx, that is the ux into vx, product of these two functions. So sin x into cos x is the fx, and this is odd because f of minus x is equal to minus fx, it is satisfying this condition. So the fx is odd. So if we are integrating this odd function from minus a to a sin x cos x, then it comes out to be 0. So sin x and cos x are orthogonal functions because their inner product comes out to be 0. So in this case, sine and cos are orthogonal functions. Orthogonal projections. Next topic is the orthogonal projections. So its definition is, let us consider V be a vector space and U be a subset of V is any subspace of V. A linear mapping from V to U is called a projection of pi square, that is pi dot pi is equal to pi the projection matrix p pi which exhibit the property p pi square, that is equal to p pi. This is nothing but it is the definition of the projection of a orthogonal projection, normally a projection of a vector space V. In one dimensional, what happens if the projection onto a one dimensional subspace? If our subspace is of one dimensional, then assume we are given a line that is the one dimensional subspace through origin with the basis vector b r to the power n. So this is the line from the origin with the basis vector b r to the power n, that is the line is one dimensional subspace u r to the power n spanned by b. When we project x r to the power n onto u, if we are projecting this vector x on u, this is the projection on u, we seek the vector pi ux belongs to u that is closest to the x. So for this projection of x on this u, we will find the closest vector. We will find the closest to the x, that is the pi ux. So this will becomes our projection. So projection of x, that is the two dimensional onto a subspace u, which is a basis vector b. So this will diagram representing the projection of x on a basis vector. So some properties which our projection pi ux satisfies. So first properties in this is the projection pi ux is closest to the x. As we have seen in the definition also, we will seek the vector pi ux that is closest to the x. So pi ux must be closest to the x, where closest implies that their distance, the magnitude of the distance from x to the pi ux, that means this distance, that should be the minimal. X to the pi ux distance should be minimal. So we can say that the pi ux is closest to the x. And it follows that the segment pi ux minus x from pi ux to x is orthogonal to u. That means it should be orthogonal to the u. The orthogonality conditions involves that yields that pi ux minus x, inner product of pi ux minus x, that means this segment of inner product of this segment into the basis vector, that comes out to be 0. That will be the condition of orthogonality. These two inner products comes out to be 0. So this was our the first property of the projection pi ux. So the next properties of this projection pi ux, that is the projection pi ux of x onto u must be an element of u and therefore a multiple of the basis vector b that spans u. That means our projection is nothing but it is the multiple, any real number multiple, lambda is any real number of our basis vector b. This is the second property of the projection pi ux. So lambda is the coordinate. If this condition holds, pi ux is equal to lambda times b, then we can say that our lambda, that is the real number, is nothing but that is the coordinate of the pi ux with respect to the basis vector b. So this is the second conditions, second property of projections. Now, now using these two properties, we can find more results in this regarding projection into one-dimensional subspaces. So first of all, we can find our coordinate lambda using those properties. How we find those coordinate lambda? As we know that the condition of the orthogonality exists, that means x minus pi ux segment, this segment, x minus pi ux segment, this segment is orthogonal to this vector b. So their inner product must be 0, this condition. Now pi ux is lambda times b. We will use that property also. Pi ux is lambda times b. So in place of pi ux, we will put lambda b. And their inner product should be 0. Now, using the properties of the inner product, we can expand the inner product as this. That is the inner product of xb minus lambda times of inner product of b into b. That comes out to be 0. After solving, we can find the lambda as the inner product of xb upon inner product of b into b. And inner product of b into b, that is nothing but it is magnitude of b square. And inner product of xb is also equal to inner product of bx. That is also true. So we know that the basic definition of the inner product, that is b transpose into x. So in above, we can write it as b transpose into x. That is the final formula of our coordinate lambda, that is b transpose x upon magnitude of b square. If any case exists, then when magnitude of b is equal to 1, then our coordinate lambda of the projection is given by b transpose into x. So this will be our projection if and only if this magnitude comes out to be 1. This magnitude comes out to be 1. So then the coordinate lambda will be b transpose into x. This is the first result of the coordinate lambda. So how we use this properties in order to find the coordinate lambda? In the next result, we will finding the pi ux. That means finding the projection point, where the projection point exists. That means actually where the pi ux will be in this curve. We will find this in the next result. So the next result, since we know that the property, that is pi ux is lambda multiple of the basis vector b, that is lambda time b, and it is also can be written as, we know that lambda formula from the above result, we can put this, that is the inner product of x into b upon magnitude of b square into b. This x into b inner product can be written as b transpose into x upon magnitude of b square into b. So we have seen that how we find the pi ux, the point, using this lambda coordinate. So this will be the formula. So length of the pi ux, what will be the length of pi ux? So length of pi ux, that is the magnitude of pi ux, that is the magnitude of lambda times b, magnitude of lambda into magnitude of b. We will find the magnitude of lambda and into magnitude of b. So the projection is of length is mod lambda multiple times of length of b. So we can find the length of projection and the projection point also in the second result. So we have seen two results, how to find the coordinate lambda and how to find the projection point pi ux. Nextly, we will see the finding the projection of matrix p pi. How to find the projection of matrix p pi? That in the definition of the projection, what we have seen that pi ux is nothing but it is p pi into x. That means projection is linear mapping property. So pi ux is equal to lambda b, that is equal to b into lambda, almost same. And we use the formula of lambda here. This is b transpose into x upon magnitude of b square. And if we collab these to b into b transpose upon magnitude of b square and x as single entity, then we can write p pi x, that is equal to b into b transpose upon magnitude into x. After cancelling x terms, what we got, that is p pi. So in the third result, how we have find the projection matrix p pi using this property. So in all these results, first of all, we have find the coordinate lambda, then what is the projection point pi ux, and the length of the projection pi ux, and after that projection matrix. In all these things we have find using the properties of the projections. So let us take an example regarding the projection of single dimension. So the example says what is the find the projection matrix p pi onto the line through the origin spanned by a basis vector b, that is 1 2 2 t. B is a direction and a basis of the one dimensional subspace. So we know the formula of the projection matrix p pi. Directly we are using this formula, that is b into b transpose upon magnitude of b square. So magnitude of b square, that is comes out to be root into 2 square plus 2 square 1, that is comes out to be 9. Okay. So b 1 2 2 b transpose, after doing this we will go to our projection matrix. This will be our projection matrix p pi. Now let's choose a particular x to see whether it lies in the subspace spanned by B or not. Now we are checking that our the projection matrix is spanned by B or not. So for x, let us consider a random x, that is 1 1 1 transpose. The projection is, we know that p pi ux, that is p pi into x, from the definition of the projection, that is the projection matrix into the vector x. So 1 upon 9, this is the projection matrix we have find in the result p pi into x, that is 1 1 1 transpose, this is, and we got the result 5 10 10. If we common if we taking common 5 from here, then it will come out to be 1 2 2. So this is the span of our basis vector b. So we have also checked for any vector x that comes out to be in the span of the basis vector b. So this was the whole concept of the projection onto the one dimensional. In the next topic we will take the n dimensional projections. So this was from my side in the presentation. Am I audible, sir?
Yeah. So this is yeah. So this thing is used in uh, this projection representation is also useful. Yeah. So this is used in the